Okay, pre-calc students, welcome to the flip lesson. In this lesson, we're going to be focusing on quadratic sequences. So far, we've dealt with arithmetic sequences. Our focus today is going to be on quadratic sequences, and specifically what we're going to be doing is using difference arrays to find explicit formulas for these quadratic sequences. And so obviously, since we've dealt with arithmetic sequences before, I'm going to start with that and show you that actually what we've been doing in finding common differences in an arithmetic sequence is the foundational step in finding quadratic sequences, and that the approach we're going to use is essentially the same. And so here we have an example where we have the sequence 1, 4, minus 2, minus 5. If we were to take any term and subtract the preceding term, we're going to find what is known as the first differences, and in this particular case, all of the first differences are the same, they are constant, and this confirms for us that this sequence is in fact an arithmetic sequence. And then what we're able to do is use the first difference, the constant value minus 3, that is going to be our common difference. We're going to substitute this into the A of n formula in order to find an explicit formula for the nth term of this arithmetic sequence. So I substitute that in. Obviously we have 4 as our first term. Simplify the expression and we're left with 7 minus 3n as our explicit formula, and this of course if we were to graph this would produce a line, of course with a limited domain, but the function is linear. And so if we basically take this idea of differences, we can extend that to quadratic sequences. And so here we have a sequence 4, 7, 12, 19, 28. I'm going to repeat the process. We have our first differences over here, and what you can see with the first differences is that they're not constant. But what you should also be able to see is that actually the row of first differences are themselves an arithmetic sequence, and if we were to find the second differences, they yield a common constant term. In this particular case, that term is plus 2. And so what this allows us to know is that the first differences are not constant, but the second differences are. And so what we have here is a sequence which can be explicitly expressed in quadratic form. And so the nth term is going to be, the formula is going to be of the form an squared plus bn plus c. And so what I'm going to do now is I need to be able to solve for the 3 unknowns. What are the coefficients of the squared term, the linear term, and the constant. In order to establish my system of equations, what I'm going to do is substitute n equals 1 into this expression. It's going to produce a plus b plus c. N equals 1, of course, represents the first term. And so we know from our sequence that the first term is 4. And so we have 4 is equal to a plus b plus c. We can repeat that process with n equals 2. So I've substituted 2 into the place of n. It yields 4a plus 2b plus 2c. And of course we know that our second term, n equals 2, is 7. And likewise for the third one, keep in mind that we didn't need to substitute n equals 1, 2, and 3. We could in fact have used any of the terms in the sequence. Obviously it's logical to use the smaller values just because it results in slightly less work for us, and it's slightly more efficient, but it doesn't really make any difference. So what I'm going to do now is solve this system of 3 equations with 3 unknowns. I'm going to pause for just a moment and do some of that off screen, and then I'll come back to the answer. Okay, so welcome back. So what I've done is I've gone ahead and I've solved the system of 3 equations with 3 unknowns. I began by isolating a. I substituted that value into the other 2 equations. That allowed me to simplify the system to a system of 2 equations with 2 unknowns. I distributed 3 across the first equation over here so that the two equations could line up and I could eliminate one of the variables. This allows me to solve for c equals 3. I sub back into this equation over here to yield the b value of 0, and I sub both the c and b values back into the a expression to yield a equals 1. We now have the values of a, b, and c, and we can now find our final solution, which is the explicit formula for our quadratic sequence, 1n squared plus 3. Okay, moving on. So what we're going to do now is look at the general case, and you'll be able to see that there are slightly more efficient ways of doing this. And so if we set up a difference array here for the general form of the equation, we're subbing in 1, 2, 3, and 4 to produce the a plus b plus c, 4a plus 2b plus c, etc. And we're going to generate the difference array using the general terms. And so 3a plus b is obtained by taking this term in the sequence and subtracting the previous one, just as we would do with a numeric sequence. And what we find is we get our row of first differences. The important thing to note here is that the row of first differences are themselves arithmetic, and then when we find the second differences, it yields for us a constant term, and the constant term in this particular case is 2a. And so the second difference in the general case is 2a, and so what we're going to be able to do is apply that information in order to be able to speed up the process of solving the system of equations. Okay, and of course we have our TIs to do that as well, but we need to be able to do this by algebra. Okay, so what I'm going to do is example 1, we have an explicit rule for each sequence, and so I'm going to find the first differences, and so we've got the 6 minus the 4, which is going to give us 2, 14 minus 6, which is going to give us 8, 28 minus the 14, which is going to give us 14, and 48 minus 28, which is going to give us 20. Those are our first differences. If we repeat the process, 8 less 2, we're going to get 6. 14 less 8 is going to yield 6. 20 less 14 is going to yield 6. So once again, we have the second difference being constant, and that allows us to know that the form of the equation is going to be quadratic. T of n is an squared plus bn plus c. We're going to use the general case this time to speed up the calculation, and so we know that the second difference is 2a, and so in this case we can say 2a must equal 6, and therefore we have the a value of 3. The second thing we can do, just to speed things up a little bit, you can see from the general case we have the equation 3a plus b, and 3a plus b was obtained by taking the second term minus the first. So if we look at our example over here, when we took our second term minus the first, we got a numerical value of 2, and so I have 3a plus b equals 2. We know that a is 3, and so I can substitute that in, and it allows me to solve for my b value, and then we can then go back and use this over here, a plus b plus c, which equals 4, and substitute in the other values. So we have a plus b plus c is equal to the first term, which is 4. We substitute in the a and the b values that we've already solved for, and that allows us to solve for c, which equals 8, and we have now got our explicit formula, which will be 3n squared minus 7n plus 8. Okay, and what you might want to do in an instance like this, you might want to substitute in an n value in here, let's say n equals 2, and we want to make sure that if we substituted in n equals 2, that it would produce the numerical value 6, and that's just to ensure that our formula works. Okay, so here we have example 1b. It's the same process, and so I'm going to suggest at this point that you pause the video, have a go at this yourself, and then I'll write up the solution, and once you hit play again, the answer is going to appear for you. Okay, welcome back. So if you took my advice and you went ahead and tried this yourself, hopefully you ended up with a an explicit formula for the sequence of t of n equals 3n squared. Let me just remind you quickly, we used the generalized result for the second difference being 2a. That allows us to find a. This equation, 3a plus b equals 9. You could see the first term of the first differences was 9, and of course that is equal to 3a plus b from our general term. Okay, let's move to the second example here because we've only got a few minutes. So in this particular case, you've been asked to find a recursive rule. Remember, the idea of a recursive rule is that the sequences of, the terms of the sequence are generated based on knowledge of the previous terms and a rule that relates a later term to an earlier term or terms. And so we're going to begin with the same process, and that is with first and second differences. And so I'm just going to do that very quickly off screen. Okay, and so you can see all I've done is the first and second differences. This confirms for us, if we were to do an explicit formula, this would be quadratic, but what we're after is a recursive formula. What I can, though, do is use the fact that the first differences of a quadratic sequence will themselves be an arithmetic sequence. And so in this case, I'm able to say that A1 is 2, D, the common difference is going to be 6, and using the AN formula, I am able to get an explicit formula for the arithmetic sequence. And then what I'm going to do is write my recursive formula, and my formula will be a to the n plus 1 is equal to a to the n plus 6n minus 4. And so what I'm going to be doing is to find the second term, I'm going to be taking the first term and adding the term, the relevant term from the arithmetic sequence. What we always want to do with a recursive formula is to ensure that we've got the correct formula or formula that will produce the terms of the sequence. And so I'm just going to do a quick substitution to check. And again, in the interest of time, I'll do that off screen and then just show you the working. Okay, and so what we have here is I've substituted in n equals 1 into both sides of my recursive formula. This has yielded the relationship that the second term is the first term plus 2. And so that is confirmed. 6 is equal to 4 plus 2. The third term is the second term plus 8. And there we can see that that is confirmed. And so now I can be sure that my formula is correct. Okay, and so a couple more to do here. And again, I'll do some of the working off screen. This time we're given a formula and we've been asked to generate the first 5 terms. This is essentially a substitution exercise. So t of 1 is equal to minus 2 times 1 squared plus 1 plus 1, and that's going to yield the first, and then I will use the same process to generate the other terms. Okay, and so here we have our 5 terms of the sequence, as I mentioned, all obtained by substitution demonstrated over here. Okay, so while time is running a little low, I'm just going to make sure we do not run out of time. And so this very last question here is a challenge question. You've got the background knowledge to do it, but it should extend you a little bit. We've seen one of the elements of this problem before, so I'm going to point that out, and that is you should notice the alternating sign. Beyond that, I would suggest you start with some differences, and that's what I'm going to do. Give it a go for a little bit, and then I'll come back to you in a little while after you hit play. Okay, so welcome back. Hopefully you gave this a try yourself, and what you would have realized is that what we're dealing with is a cubic because it's the third differences that yield the common difference. That would yield an expression, or rather an equation of cubic form. It would require us to generate and then solve a system of 4 equations with 4 unknowns. I'm going to show you an alternate version that you might have spotted, which is a little bit quicker than that. Okay, very quickly, what you might have noticed is that if you do 1 cubed, 2 cubed, 3 cubed, it produces this sequence, which is only one more than the given example.